Here is a cool idea that I must talk about. So when you think about direct air capture systems, there are various things like this which are flow-through systems, like the artificial tree of Klaus-Lackner and so on. And considering that the CO2 concentration in the atmosphere is only 0.04%, you can imagine that you'll have to move through enormous amounts of volume of air to capture CO2 at a substantial level. So scalability has been a big issue, and I've already mentioned several times that Iceland installed one of these monsters of DAC, direct air capture systems, which is the largest, I think, right now, and it only takes out about 800 cars off the road per year. So it's a tiny amount. So is there a way to just find natural ways of having flow through so that you don't have to design such systems and use energy to churn fans to suck in the air and spit out the CO2 free air and so on, or precipitate out CO2 and so on? Well, you'd think it would be obvious and intuitive. So this paper from a Elsevier publication called One Cell or Cell or something like this reports on a paper that imagines using trains as direct air capture systems. So here is a rail DAC car. So this is a schematic of a rail DAC direct air capture car. Air passes through intakes extending up into the slipstream of the moving train through DAC contractors mounted within the cylindrical collection chamber, while the regenerative braking energy and solar power is utilized to charge a large battery array contained in the undercarriage. So there's a battery array in the undercarriage. So they've thought about quite a few things. Captured CO2 is liquefied and stored and then offloaded at stations during crew change or fueling stops. So obviously you have here a flow-through system as the train is moving forward in this direction. So CO2 heavy air comes in. There are solar panels to get the energy to do the capture and liquefaction without going into the technical details. So there is a collection chamber, and then liquid CO2 reservoir is filled up and CO2 free air is thrown out at the back end of this. Is there a life cycle analysis to do this? Well, not yet, but you can imagine that the idea itself of using a moving train to have large flow through is a fantastic one, and I'm totally excited about that one. They also think about a locomotive emission transfer array, so LETA, for locomotive emission mitigation, which is referred to here as LEM, locomotive emission mitigation. So this system, again, zooming into this here, a locomotive emission transfer array funneling diesel exhaust into a locomotive emission mitigation car for point source locomotive CO2 emission capture on diesel rail lines. So this is not direct air capture, but it's capturing the emission from diesel trains, so that part is also mitigated. This, in addition to sustainably sourced electrified rail, will broadly enable rail as the first carbon neutral mode of heavy transport, in addition to a primary carbon negative role in the removal of anthropogenic CO2 from the atmosphere. Behind the locomotive consists several rail DAC cars perform the primary mission of removing CO2 from the ambient environmental air by direct air capture, as we look at. Stupid. Okay, I'm not going to edit these outbursts. My computer goes suddenly to sleep, as I mentioned in the previous podcast. If you know how to fix it, let me know. It's an HP Elite book or whatever. Okay, so here they offer some more information. Tons of CO2 mitigated in trains per day. So regenerative braking CO2 mitigation potential per train per day by mode and utilization. So they look at regenerative braking CO2 mitigation potential, and these are the numbers in the tons of CO2. So there is the electric method where you're going directly from regenerative braking energy. So when you brake, for whatever reason, there is heat generated because of friction, which you are obviously using to brake, but there are methods in which that heat can be used to regenerate energy, which is what is called regenerative braking energy. If it can be fed directly to the grid, or it can be used to charge a battery and then used for propulsion. You can use diesel RBE to a battery and propulsion. You can do electrical vehicles, so RBE to battery to propulsion, net grid, and direct air capture. So you get the idea. So here various requirements: step-up transformer would be required, battery array is required if you want to charge a battery and use it for propulsion, rail vehicle is required, of course, in this case, and rail DAC cars are required for this. So that would be about 100 to 150 to 200 per megaton of trains. Multiple DAC modules required here, 20,000 per megaton, and so on. So numbers may be debated, or people will respond to this with some details of why this may be an overestimate or an underestimate and so on, but I'm just going for the idea and its remarkable novelty in terms of using moving systems, which are public transportations. And elsewhere in the book called How Bad Are Bananas, we looked at how moving from a car to a train can save CO2 and so on and so forth. So nobody can argue against public transportation systems like trains, and already they are better for the environment in terms of removing cars from the roads, but using these methods they can also become part of the negative emission technology, or CCS. So this figure looks at rail DAC scaling and global CO2 harvest potential. Again, take the numbers for what they are. I'm just reporting them. So here, traditional rail cars versus rail DAC manufacturing in North America only. So they are looking at history in terms of thousands of rail cars produced and what they see going into the future. And again here, thousands in terms of the total rail car, total rail DAC cars, direct air capture cars, and these are the rail DAC car production. So obviously the numbers will keep accumulating because of the life cycle of the trains being longer than so life cycle replacement begins at some point here, for example, which flattens the total number of DAC rails, right? So just if you look for this, then the potential in gigaton CO2 is over time, starting very early in 2030, would be about less than half gigaton CO2. By 2050 you can hit 2.9. By 2075 you can hit 7.8. So even if these numbers are optimistic, it doesn't matter. The technology and the idea is fantastic. This is again for North America only. So rail DAC global CO2 harvest potential per year, and this is rail DAC cumulative global CO2 harvest per year. So how do you we know, we talked elsewhere about the warming being related to cumulative carbon, so the next trillionth ton has to be avoided, as Miles Allen always says. So we have to track cumulative CO2 because that's what we need to track for global warming targets like 1.5 and 2 degrees C and so on. So here is the IPCC low requirements in terms of the global warming targets, which is 100 gigatons. So the rail DAC system is here going to hit that number somewhere around 2064, and the IPCC mid scenarios give you 550 gigatons, which this system will hit in 2123. So by 2100 this is expecting to hit 369 gigatons of cumulative CO2 harvested. So impressive numbers and impressive new idea on how to create flow through for a DAC, which is critical. How does it compare to the estimates made by Rogel's paper in terms of range of global emission pathways in scenarios consistent with likely chance of 2 degrees C or medium chance of 1.5 degrees C. So this is something like 67%, I think, and this is about 50%. Just check those numbers in terms of probabilities. So here are the gigaton CO2s. We are already behind. Typically baseline of 2010 is used, and if you look at where we should be by 2010, we are already behind, but where will we hit these numbers? So likely 2 degrees C pathways give us more time and more CO2 allowances for a while till 2065 in terms of hitting zero and then having to go negative. This we argued that integrated assessment models tend to rely on technologies that are still not there. So this is, on the other hand, medium chance of hitting 1.5 degrees C pathway would require that we hit 50% of the gigaton CO2 drawdown by 2032 and hit zero emissions by 2050 and then go negative. So you have to compare these numbers cumulatively with the numbers proposed here. So this is global CO2 harvest potential for train DAC, and it will give you 2.9 gigaton by 2050. So looks like a small number, but they estimate how to scale this up to global trains and estimate how many trains will have to keep running all the time. Of course, they are transporting people and goods and so on, and also doing this DAC at the same time. But you can easily argue that they could be a big part of this portfolio of drawing down CO2 as we go forward. So just take the idea for what it is. Maybe you're not as excited as I am. I love trains, and if trains are doing DAC along the way, I would really be excited to ride such a train more and more, right? Okay,